Hi, I'm Nathan Song, and this is another video covering Test A, Paper 2, number 12. So right off the bat, we know that this is going to be a 19-point question on day 2 of our examination. And the question tells us to consider the function f of x equals ln x over x, where the bounds are from 0 to e squared. Well, first off, we want to underline these facts because whenever you encounter a 19-point exam and the question itself is just one-liner, those are the two most important things you have to pay attention to, the bounds especially. So let's get off to it. Part A says solve the equation f prime of x equals 0. So what the question wants us to do is find at what points does the derivative of this function be equal to 0. Well, we know that the derivative of the function is 1 over x times x minus 1 times ln x over x squared. And this tells us that 1 minus ln x over x squared is going to be f prime of x. We want to find the critical points here, meaning that 1 minus ln x is equal to 0. This bottom part doesn't matter that much because it's just x squared. So 1 minus ln x equals 0, where that's going to be when x is equal to e. And from the bottom part, we know that x is also going to have a critical point at 0. Well, we know that 0 can't be a critical point because x has to be greater than 0, strictly, meaning that our only critical point is e. Okay, now part 2. Hence show that the graph of f has a local maximum. So let's define what a local maximum is. A local maximum is a point where the slope of the graph changes from increasing to decreasing. So it goes from up and then it goes back down. Now, how can we determine this? Well, we've already figured out what our derivative function is. So let's make one of those nice line graphs. I find these very helpful for determining slopes changes. We know that anything below 0 is going to be undefined. It's x squared down here. Anything divided by 0, undefined right off the bat. And if it's somewhere between 0 and e, let's choose a number. Let's say 1. 1 minus ln of 1 is just 1 over 1. So we know that this is going to be positive. Anything greater than e, let's say e squared, that's going to be 1 minus e squared, which is 1 minus 2, or just negative 1. So negative 1 over e squared, that's going to be negative. So we see that it goes from increasing to decreasing at e. So we know our answer. But if you want to present this to the HL exam, then you have to word this differently. You have to say that as f prime of x is greater than 0 when x is less than e, and f prime of x is greater than 0 when x is greater than e must be a local maximum. So that's one of the things about the HL exam. You can't just settle for having this line. You have to explain it using words and the correct terminology. So next, let's go to part 3. Write down the range of the function f. Well, the range is the maximum and minimum f of x value or y value that this function can have. We know that e is at a local maximum. And we also know that this is the only maximum of this function. After all, there are no more critical points, and it changes from increasing to decreasing. In other words, our greatest point is going to be when f of x is equal to e. So, greatest is f of e, which comes out to be just 1 over e. After all, it's 1 minus ln of e ln of e over e, which is 1 over e. Now, do we have a lower bound? Well, if x gets infinitely close to 0 from the positive direction, well, this ln of x is going to become infinitely large, negatively. So it's going to be like negative 100, negative 1000, negative 10,000 as you get closer and closer to 0. So the lower bound is just going to be negative infinity as it gets closer. So all we have to say is that f of x will always be less than or equal to 1 over e. You want to pay special attention to that equal to section. Okay, so that's done. Let's move on to part B. Part B asks us to find the point of inflection on the graph and determine its coordinates. Well, the second that we hear the word inflection, we should be saying second derivative. So we know that f prime of x is 1 minus ln x over x squared. Let's take the second one. F prime of x, double prime of x is 1 over x times x squared minus 2x, 1 minus ln of x, all over x to the fourth. We simplify this to get negative x minus 2x, 1 minus ln x over x to the fourth, or negative 3 plus 2 ln of x over x cubed. So you could do the math on that. If you want to slow it down a bit, that's fine. But this is our important section. Just like before, we don't need to worry about the bottom part. Bottom part, we know that the critical point is going to be 0. We worry about the top part. Negative 3 plus 2 ln of x equals 0. We find that x has to be equal to e3 over 2 to satisfy this condition. So we know that x is going to be, for critical points, 0 or e to the 3 over 2. We know that 0 won't work because x has to be greater than 0. And now we, again, draw our number line. So it's very similar, very, very similar to how we did part A, except that we're just repeating it for the second derivative. So again, undefined. And if we plug in 1 into this function, now we get negative 3 over 1. So this part is negative. And if we plug in e squared here, well then we get 1 over e cubed, or e to the sixth. And we get positive here. So we realize that this point e is a local minimum for the second derivative. In other words, this point of inflection on the graph is going to be a local minimum, but doesn't really matter. It's a point of inflection, nevertheless. So we find that x will be e to the 3 over 2, and the point will be e3 over 2, 3 over 2, e3 over 2, if we just plug in this value here. I do not believe there is a need to copy this section, this reasoning portion, over here to show that it's a critical point. However, if you want to, just for security, you could say something like, given that the second derivative of x is less than 0 for x less than e to the 3 over 2, and the second derivative of x is greater than 0 for x e3 over 2, this point would have to be a critical point, or a point of inflection. Okay, so now we've proven what point is the point of inflection, and we've determined which point that is. So we can move on to part C, which asks us to sketch the graph of y equals f of x, indicating clearly the asymptote, x-intercept, and the local maximum. So let's just draw a line here to mark off our work. And let's take note of what they said. The asymptote, x-intercept, and the local maximum. What this wants us to identify is the same things that we found. We know what the x-intercept is going to be, or we could find it pretty easily. We know where the asymptote is going to be. That's going to be at the range of the graph. And we know what the local maximum is. We know the local maximum is at e, don't we? So let's graph it. Just a basic coordinate plane. And a sketch. We know that as x gets infinitely close to 0, it's going to be negative infinity. So we could draw a straight line going up here. We know that this graph is going to intersect the x-axis when x equals 1, because ln of 1 is just 0. Okay. And if we continue this curve up until its maximum point at e, okay, then we can curve it back down, like so. So it infinitely approaches 0, but it never quite gets there. We know that this value is going to have to be 1 over e. So as you can see, my graph is not to scale, but that's fine for the AP exam. And to show that this is its asymptote, we can just draw a dotted line there. And that's it. That's our graph. Another thing that you would want to do is make a point here and erase everything up to here, marking this point as e squared, because as we know from our bounds, it's going to be from 0 to e squared. So the graph does not continue past this point. Okay, so let's move on to part D. Now consider the functions g of x equals ln absolute value of x over x and h of x, which is the ln of the absolute value of x over the absolute value of x, where x is bounded from 0 to e squared. So g of x and h of x with the bounds being 0 to e squared. First, let's sketch the graph of y equals g of x. Well, what do we know about absolute value functions? Well, for g of x, if we change x to be negative, then what this is telling us is that it's going to make a flipped graph on the other side of the y-axis, isn't it? So let's just draw a coordinate plane again. Freestyle the y-axis because no reason. But we know that g of x, at least for any value of x that's positive, is going to be exactly the same as ln of x over x, right? Absolute value doesn't change anything when the x is positive. So let's just sketch that. Now what happens when we change x to be negative? Well, if we change x to be negative, this entire thing is flipped over, like a mirror. However, since this value is not under the control of absolute value, it's going to be reversed or reflected in this manner. Not to scale, but you can see it kind of being reflected over this line here. So that's a pretty simple graph, and that's our answer for this portion of the question. And next, the question wants us to find the range of g. Well, what would be the range of g? Just looking at this graph, we see that when x is positive, it goes infinitely close to negative infinity, right? As it gets closer to 0. But if you reflect that and it does the same thing for positive infinity, well, you know that this graph is going to cover every single possible value from negative infinity to infinity. So it's just going to be all real numbers. Okay, so let's move on to part 3. Find the values of x such that h of x is greater than g of x. Now, we could go through a lot of formulas and a lot of work regarding this, but we've already used graphs up until now, so let's just keep on using them. So we can draw that and our x-axis right here. So let's first graph the graph of g of x. So this can be like that and that, just taking it right off our previous one. And now what changes for h of x? Both of these formulas are identical in every way except that this part has absolute value under the x. What does that change when x is negative? Well, it changes the fact that this is going to be reflected over the x-axis. So like this, intersecting at that point. As for when x is positive, it's going to be the same thing. Absolute value doesn't change anything there. So we can clearly see that h of x is going to be greater than g of x for all of these values. All of these values right there. So, since we know that this point is -1 from our graph before, that's the point of intersection with the x-axis, we know that x must be less than -1 for h of x to be greater than g of x. However, again, remember our bounds. We know that negative e squared will be the absolute minimum x can be. So we need to bound this correctly from negative e squared to -1. So this question is a pretty simple one, all parts included, but it makes sure that you don't forget any of the simple things. You have to remember that the point of inflection is the second derivative, that you have to remember how to reason for the local maximum. You also have to remember how to correctly mark asymptotes and recognize the connection between all of these formulas. If you didn't make the connection between part D and part A, well, then you'd be stuck and you'd run out of time. But since you know the properties of absolute values, you can use that to your advantage on the HL test to save you time and hopefully get you some more points. So that's it. This should earn full points regarding all sections. The first section, showing the derivative and each part, that was worth 5 marks. Showing for part B, doing the same thing as part A, that's another 5 marks. The only difference between parts A and B are that part B is the second derivative, part A is the first derivative. Nothing else has changed. And that's just about it. So I'll see you on the next video, and thanks for watching.